Hello and welcome to the first of a new series of videos where I'll be covering the topic of computer science and how to code. Computer science often has an emphasis on coding languages, but is more generally about solving problems. Throughout this series, that's going to be our ultimate goal, is solving problems, but I'll indeed also teach you how to code. So we'll go ahead and introduce different topics and concepts, work on understanding coding languages, cover some different popular coding languages. I'll have a number of practice problems for you when applicable so you can practice what we cover, and go over the solutions to those problems in separate videos. We'll briefly discuss some different technologies in computer science, such as AI and its impact, and I'll do my best to give advice on various topics such as why you might choose one language over another, and my personal suggestions as well. Well, we're going to cover concepts and principles for multiple different languages, so at the end of the series, you may not be a master of any specific programming language, but you will know how to code. That's because these concepts and the practices we'll cover are translatable to pretty much any coding language, and by covering some of the more popular and more useful languages in this series, I hope to allow you a better understanding of which language or even just which type of coding language you might want to focus on. I should note here that in fact you don't need to come out of this series with the intention of using programming as a practical skill, but that computer science is just so applicable to so many other fields. Maybe most obviously STEM fields, but really just about anything you can think of can benefit from some computer science training. That's simply because at the end of the day, computer science is the study of information, but really, and more specifically, it's about solving problems and using certain ideas and techniques that will help you do so. It's really the application of these ideas, which we're going to begin diving into today, that you can apply to this field and most any other, but in computational, i.e. very methodical ways. So it helps clean up your thought processes. Even if you go off into the real world and do nothing in tech, you'll have the ability to express yourself a little more correctly, more precisely, and generally having a better command of your own ideas and your language. That said, let's go ahead and get into it. Before we dive into any programming, let's talk about how computers work just for a bit. We can describe problems we might come across by using an input, algorithm, output, or solution method. We have something we want to solve, that's our input. That's our problem, right? We have the process or the instructions by which we attempt to solve that problem, and we have the solution itself, which is our output. We can describe this in any type of language as long as we all agree, whether it be in English, some other spoken language, or a programming language that we'll cover in this series. A computer, as you might be aware, can only speak in zeros and ones. You may have heard it said that things happening in a computer is just a bunch of zeros and ones, and that's actually correct. This is called a binary system, bi meaning two, since we only have two values to represent things, 0 and 1. As humans, we typically count using the decimal system, deca meaning 10. With the decimal system, we can count from 0, 1, 2, 3, and so on up until the number 9. We have 10 numbers represented because, of course, we count 0. That's also a common factor in most of computer science, by the way. We typically start counting from 0, not 1, so we'll keep that in mind as we go. How then do we represent the numbers 10, 100, or even 1,000 in decimal? Well, as most of us learn in grade school, we simply add another place to the front of our number to represent the tens place or the hundreds place or the thousands place. All this really is, mathematically, is multiplying this by 1, this by 10, this by 100, this by 1,000, right? And this is called base 10. So if we take this number, 2476, it's really just a string of numbers, 2476, but we read it, of course, as 2,476 because we've been essentially trained to do so. If we break this down in base 10, as before, we have our 1,000s place, our 100s place, our 10s place, and our 1s place in this case. So again, base 10 is actually 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. So if we were to add this up, we have 2 times 1,000, 4 times 100, 7 times 10, 6 times 1, or 2,470 and 6. That's how we get our 2,476 number when we add those together. So let's go back to binary then. are zeros and ones, right? We can of course represent the number 0 and the number 1, but how would we represent the number 3 or 4 or 5 and so on? Quite simply, rather than base 10, binary is base 2, so we can use the same logic as we did for decimal and just add more numbers in the front that represent different places. Since this is base 2, we're starting with 2 to the power of 0 given our ones place, meaning that whatever number here is exactly as it's represented, either 0 or 1. The next place would be 2 to the power of 1, our 2's place, and the place after that would be 2 to the power of 2, our 4's place, and so on. So now if we want to represent a number higher than 0 or 1, we add another number to the front. So here you can see our 1's place, 2's place, 4's place, and in this case the 8's place. We're using 4 digits. So for example, here we have 0, 1, 0. Since the 1 is in the 2's place, we can see that 1 times 2 is of course 2. Since the first number is 0, 0 times anything is still 0. And of course this first number over here is 0, 0 times anything is still 0. So we get 2. 0 plus 2 plus 0 is still 2. Using 3 numbers then, let's try 1, 0, 1. What number do we have here? The rightmost number is still 1. The second number is in the 2's place, which is 0. So it's still 0. The leftmost number here is 1 in the 4's place, so this is actually a 4. So 4 plus 0 plus 1 is 5. So 1, 0, 1 binary is the number 5. Each of these zeros or ones is a binary digit, which you may have heard this word before, a bit, right? It's just short, it means binary digit. A single digit is just a 0 or a 1, but we could really call it anything we want, like on or off, false or true, so on. So I hope this makes a little sense, but why do computers use binary? Well, it turns out that 0 and 1, binary, work out really well in relation to the real world. When working with something electronic like a computer, there's really only 2 states, either off or on. All right, it's either got power or it doesn't. If we were able to look inside a computer, you'd see that there are, in today's computers, millions of little switches inside called transistors. If there's no electricity and the switch is off, then we would call this by convention 0. Of course, if we throw the switch and turn it on, granting electricity, we would call this 1. No matter how fancy today's hardware gets, it really comes down to representing information and instructions in computers and phones, which are also computers by the way, in those zeros and ones at the lowest level. So 3 bits, as we looked at earlier, isn't really all that useful today though. So even when talking about things data-wise, we don't often use the word bit. We use the word byte. A byte is just a more useful unit of measure in computing. It also happens to be a power of 2, so 2 to the power of 3. Which makes math work out more cleanly as well. But it's just a convention agreed upon by experts years ago all around the world. So this 8 zeros represents 8 bits and the number we know as 0. And this, all ones, 8 ones here, a byte with all ones, represents the highest number we can count using 8 bits. And I'll save you the math as we were using before. It's the number 255. So there's really no need to do the math, but you could. This is the 1's place, the 2's place, the 4's place, the 8's place, the 16, 32, 64, and 128. And because they're all 1, you really just have to add all of these up, and you get 255. You could also realize that each digit, each bit, can only have 2 values. Since there are 8 bits, you could just do 2 to the power of 8 to get 256, which may be easier. 256. Yeah, with a byte then we can represent 256 different numbers, but I just said that that was 255 a moment ago, right? So how can we represent 256? Oh, that's right, because we have 0 represented as well. So in computer science, you'll get used to seeing these numbers, specifically 256 or 255, but also numbers like 1024 and the like, which is 2 to the power of 10, otherwise known as a kilobyte. And then a megabyte, a unit you've almost certainly heard of and even used in conversation before, is 1024 kilobytes, or 1024 to the power of 2 bytes. It's just over 1 million bytes. Another would be a gigabyte, which is even more massive at 1024 megabytes, which is a staggering amount of over 1 billion bytes. and it goes up even higher than that with terabytes, petabytes, and so on. Alright, now we should have a relative grasp on how a computer using binary, bits, and bytes can be given a number. How then would we use a number to represent something like the letter A, for example? Well, it turns out a bunch of people back in the 1960s developed and agreed upon a standard called ASCII. That's the American Standard Code for Information Interchange. It's a character encoding standard agreed upon by most computer scientists back in the day as a way to use numbers to represent all sorts of characters such as the letter A. Because of the limitations of computers at the time, it only contained 128 code points, which is more than enough for the English alphabet and can even include both uppercase and lowercase characters, a bunch of punctuation, and a few other, now mostly obsolete codes that we'll cover at least one of them in the future episode when it's relevant. So this is the ASCII index here, and you can see 127 is the top, but it is 128 characters because it does start at 0. You'll also see here that the capital letter A is represented by the number 65, which is 01000001 in binary. Now, of course, 128 numbers is fine if we only used English, but what if we also wanted to represent non-English characters and languages, particularly a lot of Asian languages, which have significantly more characters overall. So that's why another group of people set out to develop what's called Unicode. This is based off of ASCII, but increases its total supported characters to well over 1 million, more than enough for every language on Earth with punctuation and then some. As of this video, the current standard defines 149,813 characters and 161 scripts used in various ordinary, literary, academic, and technical contexts. There's a lot of free space there for all sorts of other usages. In fact, a number of those represent these guys as well, emojis. It may look a little different depending on what device you're using. Apple, Google, and Microsoft each have their own artistic style applied to each emoji in their library, but the reason you can send a winky face from your iPhone to your friend using an Android and them still receive a winky face emoji is because of this Unicode standard. In fact, we can view this chart by looking at a character map here on my Windows system. I have that pulled up here. So I can scroll down, you can see all sorts of characters. You'll also notice at the top here, there's a font that's selected. You can actually think of font now the same way that we looked at different looking emojis, just that they're applying different images to the same Unicode number. So if I hover over any of these characters, I can see the number that's defined for that character. For example, the letter A up here. So you may have seen this on the screen with the emoji down at the bottom as well. But in Unicode, the number associated with the character is defined as a Unicode number with the U+ prefix. But wait a minute, this says the capital A is U plus 0041. In other words, it's 41. I thought it was 65. Well, it turns out this is using another number system common to computer science called hexadecimal. Hexa meaning 6, deca still meaning 10. Obviously together that's 16. So this is actually base 16. How's that work? Real quick, let's take a look. So rather than only being able to count from 0 to 9 in a single digit, which is total of 10, right, in our base 10, after the number 9, we can use a few letters in the English alphabet, A through F. So the number 10 in decimal can actually be represented in hexadecimal as a single digit of A. 11 is B, 12 is C, 13 D, 14 E, and 15 F, and of course we include our 0, and that's how we get our 16 total. So as with our other conversions, base 16 means that the second place is actually the 16's place. Right, so 16 to the power of 1. The third place, 16 to the power 2. The fourth place in this case, 16 to the power 3. So you can see the 1's place, 16's, 256, 4096. So our 1 being in the 1's place, just 1 times 1. Our 4 being in the 4's place, that's 4 times 16. And then these are of course going to be 0. And the conversion there, 0 plus 0 plus 64 plus 1. That's how we get 65 in decimal. You can even see with only 2 additional places just how efficiently hexadecimal can represent large numbers with less digits. So I hope that all makes sense. But here's a fancy trick if not. Some calculators for example, the one on Windows even, have an option, so we can drop from either standard, scientific, or they have this programmer option here. And you can see that we can enter a number in this case we're in decimal mode, and it will actually give us conversions in hex or hexadecimal, oct, which is octadecimal, and binary. So if I were to type in the number 41, you can see that we're in decimal, so we type in the number 65, you can see in hexadecimal that is the 41. We could also switch over to there, you get 41. You can also notice when I switch to this that it allows me to use A through F, whereas if we're in decimal, those are blanked out. Same thing in binary now, it blanks out everything but a 1 and a 0. And you can also see the actual representation of that 01000001, which we showed earlier. So this is kind of a cool, handy trick. If for whatever reason you do those conversions, some calculators like this do offer that option now. So what about other information, other data, other than letters, numbers, punctuation, and emojis? How do we render an image on the screen? What about videos or sound? Well, it turns out it's still the same information in the background, right? It's all just zeros and ones after all. But the context it's used in changes the type of data the computer shows us. So this is handled primarily from application to application. In a text editor like Word or Notepad, the computer's going to interpret those numbers as characters, those binary digits. In an image editor like Photoshop or Microsoft Paint, it uses the 0-1s to interpret pixels and colors. So what do I mean by that? So here we have an image of an old school Super Mario. The grid helps show just how that character image was created. Each square represents a pixel. So if you've ever used an image editor, you may have come across the number 255 before when you were working with color. You may have even used hexadecimal before. So it turns out that each pixel on your screen has a specific value of red, green, and or blue to display a color value from 0 to 255. Each of those three values is capable of displaying every color. So all 0 is black, for example, and all white is going to be 255 in all three of those values. So on our Mario image, you can see the RGB values that make up the different colors therein. All right, so the straight 255, full red, 0 on green and blue obviously gives us red. This blue is not directly blue, right? It's not just 255 on the blue. We've mixed in some green there as well, and that gives us this particular shade of blue. Yellow, in this case, is full red, full green, no blue. And then we've got his skin tone and this brown color for his shoes and hair being represented by this amount. If we took the numbers 72, 73, and 33, it makes this muddy yellowish color if entered as RGB values. Take that same group of numbers in a text editor, according to ASCII or Unicode, is actually the word hi with an exclamation point. So each pixel can be rendered using only 3 bytes of data, right? Each of these is 8 bits. So of course, as our images, our cameras, they get larger and larger. That's why our images are now much larger storage sizes than in the past, because it is taking up more and more bits. Every pixel on your screen, every pixel on an image is still taking up 3 bits, no matter how condensed it is. So a video is simply a series of images being displayed on the screen, so quickly one after another to give the appearance of motion. Thus, an old way of calling them motion pictures makes a lot more sense now. How many images that appear per second, what's commonly known as frames per second or FPS. GIFs are, of course, smaller versions of this. And finally, audio is simply a matter of whatever was determined for each byte to represent note-wise. You might also have additional data that says how long a note should hold for, or the volume of a note, for example. But in the end, it's still all just zeros and ones. Alright, I know that I covered a lot of non-coding in this episode, but it lays a good foundation for future talks and understanding when we get into coding later on. Make sure to subscribe and please the YouTube algorithm by liking the video and leaving a comment for me. If you want to know when the next video goes live, hit the notify bell or follow me on any of my socials for updates therein. In the next video, we're going to start coding, sort of. All will be clear, I promise. Until then, thanks for watching, and I'll see you in the next episode.